My name is Arun. I am a faculty in the mechanical engineering department. I recently joined. Okay, so today I'll be giving a presentation on short peening and its effect on corrosion resistance of engineering material. But my area of specialization is surface engineering. Okay, uh, then I am doing a lot of coating, that plasma spray coating and plasma electrolytic oxidation coating. Then actually recently there are a lot of duplex kind of treatments are happening. That duplex kind of treatment means there will be two coatings they will be doing to improve the properties of the engineering component. Okay, so my area is not basically this short peening process, but I recently find short peening is interesting because the short peening, what coating I am doing, I will be doing plasma spraying and plasma electrolytic oxidation. This short peening I can do it as a post treatment or I can be do it as a pre-treatment. Okay, so this plasma short peening, either it can be done as a pre-treatment or post-treatment for my coating process. I can tremendously improve the my coating properties. Okay, so this is by my interest nowadays lies into this short peening, but I am not an expert in this short peening process, but my expertise lies in surface engineering. Okay, so today I will be giving a talk on how this short peening can be done to improve the or how the short peening will be affecting the corrosion properties of the engineering material. Also, I will be discussing in the last few slides how this method can be imparted as a pre-treatment or post-treatment for other surface modification technique to import that duplex treatment. It will be tremendously improve the properties of the material. Okay, so I'll be starting. So you all know what is a surface engineering process. What is a surface? Why we are doing for a surface engineering process? Because we all know that whatever material we are having, all this material we cannot directly use this material for the engineering application. Why we can't use this material for engineering application? Because this material does not have the adequate mechanical property or the corrosion property what we require. Okay, then actually what we need to do? We need to modify the surface of the material. Okay, so there will be multiple domains of surface modifications are possible. These are either we can do by mechanical means we can improve the property, or there will be chemical means are there, or there will be electrochemical, electricity and chemical chemistry involved, or there will be case hardening. These are the different domains of surface treatment. Okay, so in this mechanical domain what we are discussing today is short peening comes under mechanical domain. And what is chemical? What is the difference between a mechanical and chemical treatment? Mechanical, actually, by mechanical means we will be modifying the surface. Okay. What is a chemical treatment? What is the main difference between a mechanical and chemical treatment? In chemical, there will be chemical reactions are involved. By means of chemical reaction, we will be modifying the surface properties. And coming into electrochemical uh, processes, there will be electricity involved and also there will be chemical reaction involved. The synergic effect of this electricity and chemical reaction, it will be further modifying the surface of this material. Okay. Then there will be case hardening will be there. There will be plasma nitriding, carburizing, all this comes under the case hardening. Okay. So our short peening will be comes under this mechanical surface engineering techniques. In this mechanical surface engineering technique, the short peening, it is actually done at the room temperature. So we can hold it as a cold working operation. Okay. Even though this short peening, it is multiple derivatives or multiple subdivisions of short peening process are available. That we will be discussing in the coming slides. Then what is surface integrity? What is the importance of surface integrity? Surface integrity means whatever component we are getting, this component either it is comes through a additive process or it comes through a subtractive process. What does it mean? Whatever engineering component we have, the final component what we are getting, it will be passes through series of operation. The series of operation can be either it will be layer by layer deposition, or from a bulk material we will be subtracting the material and we will be getting the final product. That is meant by, that is actually what we will be getting. Okay, by doing so, this material will be going through excessive heat, or there will be some mechanical action will be happening on the material. So what is the implications of this heat and mechanical action on this material? Because whenever there is some heat or mechanical action involved in the material, there will be a lot of changes will be happening on the material. Its chemistry can change, its microstructure can change, its surface can change. There are a lot more things will be there. Surface integrity means actually, overall we'll be saying it as a surface integrity. Whatever we are producing should be having a very good surface integrity. Okay, the surface integrity means under it comes under topography will be there, mechanical properties are there, microstructural changes are there. The topography, there will be roughness are there, waviness is there, and the mechanical property hardness is there, then fatigue properties are coming, then microstructural changes, phase transformation and microstructure are there. So for a engineering component, everything will be important, okay? So that combined effect of all this property will be determining the final property, or whether it will tell whether we can use this material for the final engineering application, okay? And then we will be looking into what is topography. What is meant by topography? Topography actually, it is the deviation from the mean profile of a surface. In a surface, we can see that there will be dimples will be there will be peaks will be there will be valleys are there, okay? So this topography will be defined as, it is the deviation from the mean profile. So in a different varieties of scale, we can express this topography. There will be macro scale will be there, micro scale will be there, nano scale will be there, okay? Macro scale, it will be dots and protrusions is the example of topography, macro scale topographies that will be affecting the topography. In the micro scale, there will be pits and grooves will be there, and nano scale, there will be nano grooves and crystal arrangement will be there, okay? As we are talking how these short peening will be affecting the corrosion properties of the material, we should be knowing how these surface topography can be, how the surface topography will be affecting the corrosion properties of the material. So here actually this is a simple representation of corrosion, how the corrosion will be happening in a material, okay? As there will be, we have seen that there will be multiple scales of topographies are there. Oh, we can see that there is a protrusion in the material, or there is a scale, or there is a, what we can say, there is a dimple in the material, or there is a pore in the material. What will be happening? This material will be interacting with nature. There will be chemical and electrochemical reactions are possible, okay? Once this material will be in reacting with the surrounding, so the electrolyte will be there. So through these topographic, that these defects, that electrolyte can enter into the material and it will reach the material, and that complete degradation of the material can happen. So overall, we need to have that surface integrity should be there for the material, okay? The surface integrity, how it will be coming? It will be coming based on the process parameter. Whatever method we will be using, the process parameter determine the final surface integrity of the material. Okay, so what is a short peening process? Professor Mario already discussed what is a short peening process. What is actually short peening process? Here actually, the basic definition, we will be having a hard ball will be there. With this hard ball, we will be impinging on a surface. As the ball will impinge on the surface, what will be happening? There will be some deformation. The surface is getting deformed. As the surface is getting deformed, what will be happening? The bottom layer, the deformation, there will be layer will be there. Bottom layer, it will be to pull this upwards. So there will be compressive stress will be happening. Okay, basically there will be that deformed layer will be in a compressive state of nature. Then the bottom layer will be in a tensile state of nature will be happening, okay? So this is basically what happen when a ball will be, hard steel ball will be impinging on a surface. Hard steel ball, it can be ceramic also, okay? So this is basically short peening, how this short peening will be happening. When there will be multiple impact will be happening, there will be a series of collision is happening, okay? So first particle will be impinging on the surface, then there will be time lag, then the second particle will be happening. So basically what we will be getting is a uniformly compressed layer will be forming on the material, okay? So that is basic form of this short peening, and this short peening we can classify into different classifications. It can be short peening will be there, laser short peening will be there, then ultrasonic short peening will be there, then ultra nano surface modification techniques will be there. Okay, I'll be briefly explain what are these techniques. In the short peening, actually there will be hard ball will be there. This hard ball will have high hardness and rigidity will be there. That means it won't deform that easily, okay? This hard ball will be forcing towards a material that we want to modify, okay? We can do this either two methods, either we can using a compressed air, we can force this particle into the material, or by means of a mechanical wheel, we can force this material, okay? And this is a single short peening method, and also we can do gradient short peening method. That means once we did a short peening on the surface, again we will be doing again we'll be doing the short peening with some changes in the parameter, okay? So multiple short peening methods are possible. And coming into laser short peening, here actually we will be using high intensity laser, okay? Pulsating laser will be used, and the laser we cannot directly apply on a surface, okay? So that there will be two medium should be there. Once actually there should be an absorption medium will be there, that may be opaque or some metallic pieces will be there, that will be keeping over the surface, and there will be water layer will be there. Okay, so once two layers are there, we will be passing the laser onto this material through these two layers. Actually, what will be happening? There will be ionization will be happening. Because of this ionization, there is a plasma generated, and this plasma, it will be formed as shock wave on the material, and this shock wave will be compress the material. Then there will be some plastic deformation will be happening on the material, or there will be compressive stress will be imparted on the material. Okay, that is laser short peening. And there will be ultrasonic short peening will be there. There will actually that we will be making use of ultrasonic sound radiations to force this particle to the material, and we will be getting the final short peen surface. These are the comparison of different short peening techniques. Actually, there will be short peening will be there, laser short peening, ultrasonic short peening, and high pressure water jet short peening. In high pressure water jet short peening, what we will be doing? We will be high pressure water. We will be forcing towards a material, and the impinging of this water droplet, it will enhance the property. While seeing all these methods, we can say that that most effective method, or the method which having highest depth of influence, will be having this laser penetration. Okay, this laser short peening will be having that highest influence of this depth profile. Okay, it will be more going to the depth, and it will modify the property. And while seeing this roughness profile of the material, we can say that normal short peening will have highest roughness compared to other processes, because there will be physical impinging of the hard bolts will be there, and it can produce higher surface roughness. And actually, what is the mechanism of short peening? How this short peening will be work? Actually, short peening is surface hardening mechanism. Surface hardening mechanism means when this steel bolts will be impinging on the surface, there will be that will be surface hardening will be happening. Surface hardening, or there will be plastic deformation will be happening. This plastic deformation, actually, it either two ways, or it will be a combination of two ways. That means there will be microstructural changes will be happening, or there will be stress hardening also happening. Microstructural changes means that microstructure, there will be dislocation multiplication will be there, or there will be some texture alignment will be there. The texture will be new texture will be forming, or there will be new grain, like nano grain size will be forming. And in the case of stress hardening, there will be residual compressive stress will be forming on the material with the good thermal properties. So these are the basic mechanism how which this strengthening will be happening in this short peening operation. Okay. And basically, the process parameter, we have seen that the surface integrity is very important, and this process parameter will tell the surface integrity. Okay, so the basics, these process parameters are short size, short material, air pressure, impact angle, distance from the nozzle, element intensity, and exposure time. Okay, the short time means like what is the size of the particle will be taking to impinge the surface. And short material means usually it will be hard steel ball, or it will be ceramic ball, or we can sometimes will be using some glass particle. All these things we will be taking for us short material. Then what is element intensity? It is actually industrial term. It will be telling how much kinetic energy will be there. What is the kinetic energy of the impinging particle on the surface? That will be expressed by this element intensity. And there will be one more term will be there. That will be the surface ratio. What is the pore to that total surface ratio? That is also important parameter. Then there will be exposure time will be there. Then impact angle, air pressure, all these parameter will be finally affecting the properties of the short peen surface. So basically, here in the study, I am only discussing about the light metal. Most of the discussion will be on light metals. Okay, basically aluminum, titanium, and magnesium. Here actually these are how these. What is the effect of short peening on the different alloys? Okay, we can see that 2124 T851 aluminum alloy, the surface roughness, actually there is huge, we can see that after this short peening there is a huge variation in the surface roughness. It is from 0.75 to 7.20. And another alloy ALSI is 10 mg, we can see the residual stress 7.75, 7.72, it is minus 152, and there will be 7475, that maximum residual stress is 0 to 45, and the micro hardness 65 to 145. As our today will be concentration on how it will be affecting the corrosion. Actually, we know that this short peening, basically it will be changing the microstructure of the material, and there will be inducing some surface defect, and there will be residual compressive stress, and also there will be what we can say, there will be some roughness effect also will be imparting on the material. Okay, so these process parameter or whatever this, because of this process parameter, we will be having some material with some residual stress or some micro hardness, some grain refinement or some roughness profile. Okay, these profile will be tell how this material will be behaving in a corrosive environment. Okay, that we need to look in the coming slides. Okay, basically what will be happening means, what is the role of surface roughness? The surface roughness actually, basically in a corrosion point of view, will be saying more the surface roughness, it will be more prone to corrode. That means there will be more area will be there to corrosion media to attack. And in the case of high compressive stress and grain refinement, we can say that grain refinement actually sometimes it will be positively affect the corrosion and sometimes it will be negatively affect the corrosion. But in a mechanical point of view, the grain refinement will be good for the mechanical properties. Okay, and how these residual compressive stress will be affected by these corrosion properties. Okay, that all we need to look in the coming slides. So now we'll be seeing how these short peening parameters affecting the roughness values. We have seen that as a corrosion point of view, the roughness, the micro hardness, the grain refinement, that are the thing that will be more that will govern how the corrosion resistance of the material after short peening. So we'll be seeing how this short peening parameter will be affecting on the roughness values. Okay, we have seen there will be multiple short peening parameters are there. So here we can see the first diagram on the left side. So it is plotted between the short peening pressure versus roughness profile. Okay, so here we can clearly see that as the short peening pressure is increasing, what is happening? All the roughness parameter, these SA, SQ, SP, SV, all are roughness parameter. Basically, SA will be the average surface roughness. Okay, these all the roughness parameter will be increasing as the short peening pressure is increasing. So we can say that there is a direct correlation between the short peening pressure and the roughness of the material. And just the adjacent image, what it is showing will be that how that short peening duration will be governs the surface roughness. Here also we can see that as the duration, that we'll be doing this short peening for more number of time, then what will be happening? Initially there is a sudden increase. So the slope of that change, we can see there is a sudden change in the roughness values will be there. And finally we can see that even though there is a change from 180 to 300, that slope of the curve is decreased. That means there is not much, it is almost getting stagnated. Okay, so these are individual parameters that will be affecting the surface roughness. Later, like people will be using these analytic techniques, that is FEM studies and other experimental studies, they could find out that they will be coming up with how these roughness parameter, how these multiple parameter will be affecting the roughness values of the coating. Multiple parameter means how the size of that ball and how the velocity of the ball, and they will be finding out they will get some empirical relation, like if the size of the ball is high and the velocity of the impingement is less, that means velocity, how the velocity at which we will be forcing this particle is low, then actually we will be getting a surface profile of very low Ri value. At the meantime, if you are increasing the size and increasing the pressure, then actually the surface profile will be, Ri value will be very high. And also there will be another parameter like the distance between these, that standoff distance or the distance between the nozzle and the material, it is increased and the area of also increased, then we will be getting a low surface roughness. Okay, whatever all these parameter, that working condition will be affecting the surface roughness, and the surface roughness will be affecting the final corrosion properties of the material. The next property will be the residual stress, how the residual stress will be affected by these parameters. Okay, here actually the left image, it will be plotted between the, it's shown the short size on the residual stress. That means in this study they have used different short size. They varied the short size from 0.1 to 0.8 and they have checked how these residual stress are varying. As here also they got a positive correlation. As the size is increasing, that residual stress value is also getting increased. On the adjacent image, they have seen the influence of short peening duration on the residual stress. Actually here they also get a positive correlation. As the time is increasing, duration is increasing, there also the residual stress is getting increased. But the trend will be, residual stress won't be keep on increasing. Initially it will be increasing, then it will be getting reduced. And also it won't monotonically increase. That when we are increasing these parameters, actually what will be happening is that maximum value of residual stress will be 50 to 60% of the sigma UTS of the material. Beyond that we are increasing also, it won't get increased. Okay. So these are the how this process parameter will be affecting this residual stress values. Then there will be how these hardness values will be varying. The hardness values actually it is plotted between area and also the pressure. Here that we can see that the area fraction is less predominant compared to the how the pressure will be. The pressure actually it is more, then actually we will be getting more surface hardness. And this is actually another study here actually they have keep this velocity 50 meter per second and they varied the duration from 2.5, 5 and 10 minutes. Okay, they varied the time and by keeping that velocity constant. Actually what happened was like uh, actually this short peening process is a cold working operation and we can see that there will be cold working will be happening and there will be some stresses will be imparting. Actually once this time is increasing, what happened was a reverse kind of phenomena happened. The reverse kind of phenomena will be there is a softening mechanism happened. That means because of this high duration of time there will be lot of heat generated and because of the heat there will be softening mechanism happen. So here actually we can see that just beneath that layer that hardness value of the 10 minutes time will be lesser than that of the 2.5 meter time. But actually in the case of 10 minutes we can see that the depth profile will be higher. That means it will having a huge impact on the depth. Okay, but actually immediately just vicinity of the surface layer that 10 minutes duration it causes a softening effect because of the high temperature. This is actually how the deformed surface layer on corrosion, how the deformed surface layer will be affecting the corrosion resistance. Actually, this one study conducted on 319 steel, 319 S aluminum alloy, it concluded that they have did the short peening, they have done the short peening and they did the uh, salt spray corrosion analysis. Then after weighing this salt spray sample, they found that these short peen sample have less damage or means that weight gain or weight loss will be less in this short peen sample compared to this non-short peen sample. Similarly, other studies this conducted on 3E12T3 aluminum alloy. Here actually exfoliation corrosion studies they have conducted and they found that because this short peen sample that red color is that normal sample and right side is the like sample that short peen sample. That left side sample we can see that there is a discoloration happen. Actually this discoloration happened at 96 hours of exfoliation studies and this discoloration and there will be bubbling will be happened on the material. Even though we did the short peening on the right sample, that actually nothing happened to that sample. Here actually small pits are there, even though the corrosion properties actually, these short peening process heavily improved the corrosion properties of this short peen sample. So these are some literature. It will be how these corrosion properties of the short peen sample is improved that I just noted down. Then what is the impact of residual stress on these corrosion properties? Actually residual stress actually it is a compressive stress acting on the material and these studies actually conducted on A6082 T651 aluminum alloy and the medium here they used was 0.6 m sodium chloride and they did that once they did the peening and laser short peening and they did these corrosion studies on sample with laser short peening and without laser short peening and they could find out that the sample with laser short peening is actually there that pit size was very small or on the contrary that sample as received sample it is having a high pit size. Okay, this is basically due to that because of the high residual stresses. When these residual stresses are imparted on the material, what will be happening when there is a external stress will be acting, it will be like compensate for, it will be actually, it will reduce the effect of this external stress. Also there will be what we can say that there is a corrosion product is, grain boundary corrosion product is formed on this surface. If there is a compressive stress is there, it will be helpful for further what you can say further we can reduce the corrosion. It won't further corrode. Okay, these are the important effect of residual stress on this material corrosion properties. Then actually this is the process of microstructural refinement what will be happening. As we know that there will be particle will be there that will be impinging on the surface. Once this particle will be impinging on the surface, what will be happening? There will be contact pressure will be happening. Once this contact pressure is greater than that of the yield strength of the material, there will be plastic deformation is happening, and this process is continuing. During this plastic deformation, it will be plastically deformed in the multiple direction, but that thickness won't be that much, it will be in the micron level only. As this process is continuous, it will be happening, there will be dislocation multiplication can happen, or there will be thin shear band or shear band also form, or there will be thin stacking fault also formed on the material. And this process is keep on continuing. This annihilation of these dislocations or defect will be formed, and also there will be micro nano cell formation, subgrain and grain boundary formation will be happening. As this new grain boundary formation happening, this will be very much affect these corrosion properties of the material. Actually, there will be people with contradictory results are there. It is stating that if there is a new nucleation site, or there will be new surface is forming, some people is claiming that it can enhance the corrosion resistance by forming a passive layer. But some people are saying that if there is a dislocation density enhancement, or there will be a grain refinement is happening, that will be act as a pathway for this ionic movement to happen. So that means that ion can easily move through this pathway and corrosion can happen. Okay. So basically, if you are simply doing this treatment, it won't be like, so we need to be do this process parameter, or we need to take this process parameter very carefully to get a good surface integrity. Otherwise, what will be happening, that many times we can see that these because of this whatever process parameter will be taking, if it is beyond certain values, we will be having some that it will be getting extremely corroded, or it will be not useful for this engineering application. And here actually, one studies they conducted ultrasonic short peening, and they use that one study will keep on increasing the beats, and they have find that there will be high grain refinement is happening due to this ultrasonic peening with a more number of beats. But actually, how these corrosion properties affected by this will be actually here. Actually, the thing they claim that due to this high surface or grain size modification, that new surface will be formed, and because of these new surfaces, there is a possibility of new passive layer will be formed on the surface, and it further corrosion, they will be restrict the corrosion. This is what happening during this process. And during these, rather than microstructural changes, there will be phase transformation also can possible during this short peening operation. Actually, this is a 10 micrograph of a unpeened and peened high strength steel. Here actually we can see lath martensitic structure with clear boundaries. Once that short peening has been done, there actually it is distorted, and there will be a lot of dislocations also formed in this structure. Okay, these are some of the case studies I have included. Actually, here corrosion behavior of surface modified titanium 13 niobium 13 zirconium alloys have been studied. Actually, this titanium 13 niobium and 13 zirconium is a potential biomaterial. Actually, this material, once we are used in the application, what will be happening? There will be, it can prone to corrosion, and also it can be to cyclic fatigue. Okay, just suppose this is beta kind of titanium alloy. We will be using this application, then what will be happening? This dental, we know that whenever they will be using this material as a dental crown, we will be chewing this, we will be daily at least 5,000 to 10,000 times, at least we will be chewing, and it is actually cyclic load will be happening. And also there will be chances that corrosion media, our saliva is a potential corrosion media. Okay, so this material is a potential material with very good application. And when we are doing that ultrasonic peening, what is happening to these corrosion properties of the material? Actually, first one is that without any peening, that has received material, then actually ultrasonic short peening has conducted with a different process parameter. Okay, here actually we can see that the process is done at 15, 30, 60, and one more time duration. And initially, we are comparing the 0 sample without short peening and 15 time duration sample. Actually, what happened is like without that as received sample showed a very good corrosion resistance compared to this 15 sample. Why? Because here actually that in this 15 sample, that grain refinement effect was minimum. Also, the grain refinement effect was minimum, but here actually the surface roughness was formed on the material. Because of this surface roughness, this material more prone to corrosion. But we are comparing the 15 times sample and 30 times sample. In this study, they got the highest corrosion resistance for this 13 times sample. Actually, in the 13 times 30 times sample, what happened was like, there is a synergic effect of grain refinement and surface roughness happened. Okay, even though comparing the 13 and 15 and 30 sample, the surface roughness was high for 30 sample, and also here actually that grain refinement was very high, and also the residual compressive stress also very high for the 30 sample, and because of that the 30 sample got highest corrosion resistance. And we are comparing uh, 60 and 120 sample. What happened was like, in this 60 and 120 sample, basically this study, what they did was, they took the titanium, niobium, zirconium alloy, and they did the uh, ultrasonic short peening. Then they varied the time duration. Actually, initially they did not do that, is 0 sample. Then they did 15. Yes, yes. They like that the periodic time period they selected, and they exposed this material for 13, 15, 30, 60, and 120 time period. Actually, that comparing the 0 and 15, what happened was like, in the 15 sample, that grain refinement effect was minimum, but there is a surface texture or surface roughness effect was there. Because of that, comparing the as received sample and 15 sample, that 15 sample more corroded. But comparing the 15 sample and 30 sample, what happened was like, even though the surface roughness was high in the 30 sample, that grain refinement and more number of more residual compressive stress formed on the 30 sample. Because of that, compressive stress and these grain refinement was more predominant than these roughness effect. Because of that, this 30 sample got highest corrosion resistance than this 15 sample. And we are comparing this 30 and higher time duration. What happened to us like, in the higher time duration 60 and 120, here actually that uh, even though that grain refinement was higher than the 30 sample, there the surface roughness effect was very higher. Means that there will be lot of surface roughness happening. There means there will be lot of impingement. There is lot of defect happened because of this impingement, and this surface roughness effect was predominant compared to this uh, grain refinement effect. Because of that, higher we here they got better corrosion resistance for 30 sample.
And, this result is actually contradicting the previous slide, a few slides back, wherein you were explaining about the aluminum alloy exposed to salt spray test.
Yes.
Wherein it was mentioned that even though the surface roughness was high, corrosion resistance was much better.
Actually there is a window period is there. So for each alloy, each processing condition, if the surface roughness was beyond certain point, the corrosion can be negatively affected. Also, the surface roughness was below some point, it will be negatively affected. So there should be between a window. It will be varying depending upon the material. Also, it will be varying depending upon the processing condition.
So, sir, are we discussing about the pitting corrosion, or are we discussing about the SCC?
I'm not discussing about the pitting like SCC. I'm only talking about this general corrosion. Okay, I am not talking about any forces involved or any SCC involved. I am only talking about that what is general corrosion, how this, when it is this exposed to a electrolytic media, or general corrosion, how that corrosion will be affecting. Not about the stress corrosion cracking. And this is another study that conducted on nickel aluminum bronze alloy. That is actually a potential it is a copper based alloy. It is having a lot of marine application. Actually, this alloy comprised of 6 to 10% of aluminum. And here actually the material, it is used in a lot of marine application, and this material having it is having a dual phase structure, or there will be predominant phases are aluminum rich phases will be there, and there will be copper rich phases will be there. When it is exposed to some media, what will be happening is there will be chances that there will be pitting corrosion can happen, or also there will be some microganglionic cell can also form. Okay, so there will be people will be doing the microstructural modification of this alloy. Here actually using the short peening technique, they modified the surface of this material. Actually they have selected the condition like SP.1 sample, SP.2 and SP.25. Actually they changed the parameter and they studied condition will be fine properties of the material. Actually what they have varied is the short peening intensity. Intensity they varied from 0.15 and 2 to actually in this material what they observed, even though the roughness is high, what they observed was like this material actually how this corrosion property will be coming because of this aluminum is there in the material. When this material will be exposed to some media, what happening that aluminum will be reacting to environment, it will be forming. And we are comparing passiveness of this aluminum oxide copper Cu2O3. What will be is the value will be aluminum oxide will be more passive than the copper oxide. Okay, so because of this formation of the aluminum oxide at the surface layer, this marine bronze it will be having very good corrosion properties. Here actually we can see that after this short peening operation, there the roughness values also got improved, and this roughness value improved means there are new surface formed for this passive film formation. Because of that, even that roughness is increased, that finally what we get is a surface sample with a very good corrosion resistance, because that more area was there for the corrosion media to attack, and that Al2O3 layer passive layer formation happened, and this passive layer formation further restrict the corrosion. This is an influence of peening on the corrosion properties of ALSI 304 stainless steel. Actually, what happened here actually, from the XRD we can see that the stress induced martensite formation is more happened. Here actually what they did, they take the sample, then did the short peening, and they did the ultrasonic short peening. In the ultrasonic short peening actually what happened was like this quantity of or the amount of stress induced martensite is higher than compared to the short peen sample. Okay, here actually when they did the corrosion studies, what they found out that even though that micro hardness values are higher for these short peen and ultrasonically short peen sample, when they studied the corrosion properties, they found that short peen sample having a low corrosion resistance than the as received sample. This is because in the short peen sample, the surface roughness was become very higher, and because of that, it was more prone to corrosion. So the new area formed, and in new areas, more corrosion happened. But in the case of a ultrasonically treated sample, actually the surface, that hardness also become higher, and also there will be the phase transformation also happen. Comparing the SP sample and ultrasonically processed sample, the ultrasonically processed sample will be having low roughness value compared to that of SP sample. So there actually we can see that here actually surface roughness played a major role. In the last case we have seen that even though it is having a very good surface roughness, very high surface roughness, it actually acts as a new surface for the passive layer formation. But here actually what happened, even the surface roughness is high, this is more prone to corrosion. Basically depending upon the material to material, we can see that the properties will be varying. Okay.
So preferably those materials which might have an oxidization tendency there, I think surface roughness might not be a criteria for
those material.
Because in the previous case, I think we were talking about again aluminum as well as the cupric oxide thing.
Yes.
In both these cases, they have a tendency to form some oxidized.
They have both tendency to form oxide layer, but actually aluminum oxide is, I think, 10 times more passive than that of the copper oxide. Because of the formation of aluminum oxide at the surface, it will further prevent the corrosion mechanisms. Okay. Basically, what we can see that, like we have seen the case of steel, we can see the case of aluminum bronze, and we have seen the case of titanium. Here actually, even though surface roughness, basically depending upon the what material will be taking, that it will be finally that will be determining the corrosion properties of the material. Okay, some case we have seen that more surface roughness, but it is more good passive film will be formed on the material, so it will be further prevent the corrosion. But in some cases, what will be happening, if that higher surface roughness, it will be act as a more area for the corrosion to happen. So basically the wall material, it will be having a very good chance, even though the roughness is higher, it will be having a very good ability to prevent corrosion by forming the passive oxide layer. This is another study. They will be actually they have by powder metallurgy route they prepared the titanium 6 aluminum 4 vanadium and they have did that short peening operation. Actually here what happened was like comparing the non-short peened surface, the short peened surface actually there will be grain refinement happen and also increase in the dislocation density also happen. And all these grain refinement, dislocation density enhancement and the compressive residual stress and effective formation of a protective layer, it enhances the corrosion properties of this material. Basically what we can see that the grain refinement, what will be happening, that grain refinement happening, some cases these grain refinement, it will be act as a, it will be good for the corrosion resistance property, but actually in some cases it will be, there will be more diffusion of ionic species will be happening and there will be more corrosion will be happening. So as such we will be taking short peening operation. So we cannot say that how it will be affecting the corrosion property. So it will be basically depending upon these process parameter. The process parameter, we need to optimize the process parameter very well. Then only we can get a material with a very high corrosion properties. Otherwise, we can say that mechanical property that it will be anyway that because of the residual compressive stress, we can say that it will be it will have very good fatigue resistance property. But for a electrochemical corrosion reaction to prevent, we need to optimize these process parameters such a way that so it should be in a window period. Period or it will be below the window period, we will be getting a material that will be more prone to corrosion. Okay, that will be happening here. So actually, so nowadays people will be okay. Nowadays, what people are doing now, there are a lot of aluminum or light metal. What they will be doing, they will be doing for duplex treatment. Duplex treatment means actually they will be combining multiple coating operation to get a final engineering component. That means in order to get a component with a desired property, they will be combining multiple operation. Okay, so in the recent literature we have seen that the short peening operation is a potential pre-treatment or post-treatment operation for many coating operation. Here what they will be doing, they will be doing actually they will be taking a material and they will be short peening the material and they will be doing the coating operation on this material and they will be checking how the properties are varying. And sometimes what they will be doing, they will be doing the post treatment. What means they will be producing the coating on the material and once the coating is produced, they will be impinging this coating with this short peen material and they will be checking how these coating properties are affected. Basically coating, we can see that there will be basic classification, there will be two types of coating will be there. There will be one is deposition coating. Deposition coating is nothing but we will be depositing some layer on the other material and one other kind of coating will be conversion kind of coating. That means conversion means that surface layer itself it will be converted into a coating. Okay, so if you are seeing that adhesion properties of the layer, that conversion coating can have better adhesive property than the deposition kind of coating. Okay, here I have included 2-3 case studies where actually the duplex treatment have been done to improve the properties of the material. Duplex treatment is actually they actually plasma electrolytic oxidation they have conducted and these short peening operation they did before the plasma electrolytic oxidation and in one cases they did the plasma electrolytic oxidation and after that they did that short peening operation and they compare the property, how the properties will be varying. And the last slide I have included how these plasma spraying operation they conducted on steel and they did that post short peening operation and they checked how the properties got varied. Okay, so I'll be discussing these things. Duplex treatment. Actually here actually the first case we'll be discussing on the coating was formed on AZ31 magnesium alloy. Okay, here actually what they did, they varied the pre-treatment conditions. Okay, so basically I'll be give a brief introduction about this. What is a plasma electrolytic oxidation? It is a electrochemical surface modification technique. What do you mean by electrochemical surface modification technique? That means there will be electricity involved. Because of the electricity, once we passing the electricity, there will be chemical reaction happening. Okay, so basically this coating will be most favorable for light metals such as aluminum, magnesium, titanium, niobium, zirconium, and we'll be keeping this material as anode and we'll be keeping this material as anode and we will be passing electricity through this material and we'll be dipping this material in a favorable electrolyte. Basically it will be alkali based electrolyte. Okay, so once the electricity will be passed, that electrolyte species will be splitting and ionic dissolution will be happening. That metallic ion will be tries to move out and the other species, so OH minus and other species will be tries to move in and it will be interacting at the surface and there will be oxide layer formation will be happening. This is actually this basic of plasma electrolytic oxidation, and we can see that the right image, something is glowing. Actually, that is actually plasma formed during this process. How the plasma will be forming? As we know that this ceramic layer, it is non-conductive in nature. Okay, so once the initial stage when we are passing the electricity, it will be conductive in nature because the surface is metallic material, aluminum is there or magnesium is there. As we are passing the electricity, what will be happening? That there will be ceramic layer will be that Al2O3 or Mg2O3 or TiO2 is a ceramic kind of layer. That means it won't conduct electricity that easily. Okay, once this ceramic layer will be appeared on the surface of the metallic material, what will be happening? It will be further prevent the flow of current. Once that flow of current is prevented, but anyway we are supplying huge current to this material, so there will be weaker region in the material will be there. That weaker region means there will be material with resistivity change will be there in the material. So those surfaces with the resistivity change, that will break. This breaking will be physically we can visualize as a avalanche of electron. That means you can see like that right side image, it will be glowing. Okay, so this is the basic coating formation during the PO coating. Okay, as we keep on increasing this current, this coating portion formation will be keep on happening and the thickness of the layer will be increasing. And we can physically see that how the color of this arc will be changing. Initially it will be in a light color arc, and finally we can say it will be in a orange red color. That means the intensity of the arcing is very higher as the thickness increases. This is the basic of plasma electrolytic oxidation. And in this study what they did, they have taken sample. One sample they polished the sample, and one sample they ground the sample. That means they imparted some roughness on the material, and other sample they treated with short peening. And all these sample they have taken for this coating method. And what they observed was like, here actually that voltage versus time curve was given, that actually represent how the process is happening. So how the voltage will be varying across, because we are applying a current. So basically current means there will be voltage changes will be happening, and we plotted the voltage versus current. Here we can see that there is not much, that shape of the curve is same. That means even though we imparted some pre-treatment, it does not change the overall coating formation process. But we can see that the curve, that SPPO curve, we can see that the initial stage, the slope of the curve is little higher. That it indicating that some physical changes are happening for this coating. Either it can be more amount of dissolution will be happening, or more passive layer formation is happening. Okay, so some chemical or physical changes will be happening at the initial stage. Okay, so once they studied the coating, they have seen that the thickness value variation, the higher thickness is uniform thickness is they obtained for this SPPO coating. Okay, why they got a higher thickness coating? Because the surface roughness values are higher, so there will be more site for this reaction to happen. Okay, so there will be more anodic dissolution happen, and there is more reaction happen. That is why that finally the coating thickness increased. By comparing the porosity of the coating, basically that that avalanche of electron means that breakdown of the coating, that final coating will be having some porosity on the surface. Here actually for the comparing the PPO means polished PU, and SPPO means that coating with shock peen and the PO. This SPPO, the base sample with the PO coating, that wider pores we have seen, we could able to see. But in the case of a SP plus PO, the pore size got reduced. Okay, that is a good indication that it will have very good corrosion resistance. Okay, so from this study they could understand that if you are doing a pre-treatment, that means if you are doing a pre-treatment of short peening on the sample, and they will be doing some coating method like anodization, they can produce a coating with a better property. Okay, so there may be reasons that surface roughness is increasing because of the SP layer, and this surface roughness there will be more chances that whatever coating will be formed, that adhesion properties also will be better, and also there will be more dissolution site will be there. Okay, all these property combined effect, they got a coating with a very good property. These are the corrosion studies. They got a very good corrosion curve for corrosion resistance property for this combined effect. And in another study, what they did actually, they did this short peening as a post treatment for this plasma electrolytic oxidation. What does it mean? That means they did the coating, and once the coating is done, they have treated this sample in the SP media. Okay, then they did that. First they did the coating, and this one they take the coating and they did that short peening operation. Okay, here actually they have taken three different set of sample. Three different set of sample means First set of sample will be just immediately after the coating process started, they take the sample. Then one set of sample, there will be actually three different kinds. We have seen how the sparking will be varying during the plasma electrolytic oxidation. The sparking, actually the initial state, we have seen that it is a light color sparking will be there. That is the beginning of the process. And the process will be continuing from this voltage time graph. The initially that steeper region is there. That is actually represented by a light color sparking, and there is a plateau region is there. The plateau region represented by a very dark color sparking. Okay, initially it will be in a bright color or yellow color, and finally it will be in a orange red color. Okay, orange red color means there will be coarse arcing is happening because the layer thickness is very higher. Again we are passing the current, so there will be coarse arcing is happening. Okay. And this coarse arcing, what is the specialty of this coarse arcing? This coarse arcing, the temperature will be very high, so sometimes there will be phase transformation can possible. The temperature will be exceeding some certain limit, so phase transformation can be possible at this coarse arcing region. Here actually what they taken was, they took three samples. One was actually they did operation till here, that actually they got a sample of very low thickness, and once in the soft arcing region they have taken the sample here, and one sample they have taken at the coarse arcing region. Okay, these three samples they have taken. One from the initial portion they have taken, they only run the experiment for a few seconds or few minutes, then actually once a second sample they have taken from the softer arcing region. That means they have run the sample for certain amount of time, so there will be yellow color sparking happen. And the third sample they have taken for a, they have done it for a longer period of time. That means coarse arcing happen, and these three samples they have taken for this short peening operation. And what they found out was like, so this is the first sample, that is a coarse arcing happened. Actually this is kind of a pancake kind of a structure is formed on the surface, and here actually there is a soft sponge like of structure formed, and here actually it's a thin layer of oxide layer formation happened. And once we on these surfaces, once we did this short peening operation, what happened was like that initial layer actually, it actually does not have much improvement in the property because the layer thickness was very higher. But comparing the sample, these two sample, actually one coarse arcing and the soft arcing, this coarse arcing layer, it is very hard. Once we impinge this particle onto the surface, that particle layer got destroyed because it is very hard layer. It is a appearance is like a pancake like structure, and it is very hard. Once it is hard particle impinge on the surface, it got damaged. But in the case of the soft arcing sample what we have taken, when the sample impinged on the surface, because of the sponge kind of nature, these actually softening happening. So there won't be much removal of material happen here. Okay, because of that, that hardness of this layer increased. Also the pores also become closed. Okay, so actually this improvement in the hardness and also the porosity become closed. It will be very beneficial for corrosion properties and other improving the mechanical properties. Okay, so these are the two literature how these they clubbed these plasma electrolytic oxidation and short peening, and how they got coating with improved property that rather than the single treatment operation. Then the last final slide I have included, actually this is a plasma sprayed coating they did. The plasma sprayed coating in that steel they did pure zinc coating, and B coating was aluminum coating, and third coating was zinc and 23 aluminum coating. Okay, they plasma sprayed this element on this high strength steel, and they did this short peening operation, and they could able to find out that once the plasma spraying is done, over which this short peening is done, the property goes improved. The property got improved because of the impingement of this hard particle, there will be changes in the phase also, microstructure also got changed. So the hardness values also got changed. The combined effect of these changes, microstructure hardness and also the porosity, the hardness become increased, that there are some certain phase changes also happen. This overall we'll got a structure with a very good we got a finally got a coating with very good properties. So actually rather than thinking of like doing some single coating, it is better always we can go for some duplex treatment. That means we can combine 2 or 3 different methods or 2 different methods, and we can produce a better engineering component than the existing component. Actually that is a very good innovation. So we can employ this coating for many more, we can use this short peening operation as a pre-treatment for many more coating operation. Even in the case of sputtering, we can use this short peening operation. We can do this, like we can take the sample, we can did the short peening of the sample, then there will be certain changes in the surface will be happening, then we can sputter the sample. Okay, but then what will be happening? There will be more area will be there. Also, there will be more mechanical interlocking will be happening on the sample. Okay, again we can see that should not limit for this short peening operation. We can take the sample, we can do this laser surface texture we can done. Also, we can go for this sandblasting, multiple method we can go for, and we can check how these pre-treatment will be affecting the final coating property. Also, once we did a coating, the same method we can again go for this. We can do it as a post treatment also. Once we did a coating, we can make this laser, we can do some laser surface hardening we can done, or we can do that sandblasting of the coating layer. Okay, so there will be, anyway there will be properties will be changing, and this, if the property change, that microstructure change or phase change or the hardness change is in the favorable condition, then we will be getting a very good component than the existing component. Okay.
Sir, sir, would you suggest doing the short peening process first and then going for the coating, multiple coating or single layer coating? Or would you suggest going for the coated surface first and then doing the short peening process?
Actually,
I think you have presented both these scenarios.
Yes, I presented both the scenarios. Just I want to show you that the duplexed coating always will be giving better property than the single coating. And both the scenarios we discussed, one it is did as a pre-treatment process, one we did that as a post-treatment process. Both these conditions we got coating with improved properties.
But sir, again, if you are performing coating and then doing the short peening process, will it not affect the coated layer? Because if you are trying to develop a thin film layer,
yes, it will be affecting the coated layer that we have seen for that coarse art sample. Actually, that the coated layer having a very high hardness value, and also we will be impinging a very high hard particle. What will be happening is there will be chances that there will be brittle crack will be formed on the coating. So we need to optimize this process parameter. The second case, the post short peening worked because of that surface was soft in nature and the particle was very hard. Once it is impinged, what happened was like the pores become closed, and also that hardness of the layer also got improved. If it is too thin, the first sample that they immediately they took the sample and did that actually
the
the
soft
first
arcing case.
soft arcing case, what happened will be like it will be completely damaged the coating surface. So it should have a minimum thickness will be there, and it should have some favorable physical properties.
But then more the thickness increases, there is higher possibility of this brittle thing happening on the coating. Right?
That also depending upon the surface condition, whether it is a very hard condition or it will be a soft condition, that also depends. Or that what is a phase or phase formed on the material. It is a like a very brittle phase, or it is a ductile phase, that or it is like is there any change in the phase composition happen, everything that basically it will be depending upon the phase composition.
But all this coating you're suggesting is these things can matter if we are going for conversion coating, right? Deposition coating, it might actually create problems if we go for the
Deposition coating, the third study I have included
that's plasma spray coating.
That is a deposition coating only.
But don't you think that the adhesion might be a big problem over there? I mean, plasma spray, of course, is giving the maximum
Even
adhesion.
actually, if there are some porosity and cracks because of this hard particle hitting, we can close this porosity, and then it will be beneficial for our coating.
Okay, sir. Thank you.
Sir, could you please once more explain the PO treatment process?
PO treatment is actually basically anodization only. So anodization, what we will be doing? There will be anode will be there, and there is a cathode will be there. So there is an anode will be there. This is the anode, and there will be cathode will be there, and we will be connecting the supply. External power supply will be there, and this anode will be dipping it on a electrolyte. Okay. In the anodization, what we will be doing is basically we will be taking acidic environment, or means acid will be taking, and once that electricity is passed, what will be happening? Metallic dissolution will be happening. Metal ions started dissolving, and also that from the electrolyte there will be splitting of species will be happening. H2O will be split into H plus and OH minus ions, and there will be some other chemicals also will be adding. Okay, everything will be splitting, and that OH minus ions will be moved towards the anode and it will be reacting at the interface and there is a coating formation is happening. But in the PO treatment actually here only difference is that we will be applying a higher voltage. Higher voltage means in the anodization we will be applying only up to 80 volts or 100 volts. But in the PO treatment we will be going up to 700, 800 volts. Then actually it is arcing is happening. So arcing happening means will be formed. We will be keep on applying this electricity. What will be happening? That the layer form for the current to, okay. So once current through an insulator, what will be happening? Some weak region will be there. This region it will be split. There will be explosion happen. Through that explosion the pass and again the coating keep on happening.